welcome to Unit 6, Exponential Functions, Lesson 6, Applications of Exponential Functions. Learning goals today, we're going to solve real-life exponential applications and answer related questions. Today we're going to focus on doubling, time, and half-life. So exponential functions can be used in problems with population growth, investment growth, depreciation, bacteria growth, or radioactive decay. So here we're going to talk about doubling period. We got this function here. N of t is equal to a times 2 to the exponent t over d. And this is dealing with doubling period. So you can see that my base is 2. So what does everything else mean? Alright, so N of t is a number of bacteria present after t units of time of growth. So basically, how much do I have after t time? So t must be the time in units given A. A is the initial number of bacteria. So how many do you start out with? And D is the doubling period. So how long does it take for the population to double in terms of t time? Alright, so here's an example. A biologist knows that bacteria culture doubles every 3 hours. So right away, every 3 hours, this must be my D. So I know D is equal to 3. After 6 hours, there were 10,000 bacteria. So that means after 3 hours, or 6 hours, so T is equal to 6, there were N of 6 bacteria, which was 10,000. And then here it says determine the initial size. Initial size will be your A value. So again, here's my formula. N of t equals A bracket 2 t over d. So we're going to substitute it and we're going to solve. So N of t, which would be my 10,000, so 10,000 equal to A, that's what I'm trying to solve for, so I can leave it as variable. 2 to the exponent of t is 6 over 3. 3 is my doubling period, so I can simplify that, so I get 10,000 equals A. And this is 2 squared, which of course is 4. Divide both sides by 4. And I get A is equal to 2,500. Therefore, the initial size of the culture is 2,500 bacteria. Alright, there we go. Let's look at the next part. The next part says this, the number of bacteria after 1 day. So here I know after 1 day, so I know that my t is equal to 1 day. There is an issue here though, because if you look here, however my t is in hours, so that means this is really equal to 24 hours. Since these are in hours, I've got to convert my t into hours. So I want n of 24 is equal to, use my new a value, 2,500, 2 to the exponent of 24 over 3. When I do this, I get 2,500 times 2 to the exponent of 8, and this gives me 640,000 bacteria. So therefore, after 1 day, there is 640,000 bacteria. Alright, so that is doubling period. Next one we have, that should not be 6, that should be 3. Okay. Next one, here we go, half-life. So half-life, this deals a lot with radioactive decay, or decay, and it is the period which a substance decays until half is left. And so you can see here that for this, my base is a half. It's the same as doubling period, but my base is a half. So let's define a few things here. M of t will be the amount left after t units of time of decay. T is time in units given. A is again the initial amount of the substance, and H is the half-life period. So how long does it take to get from the initial amount to half that amount? All right, so here we go. Strontium has a half-life of 25 years. So right away, half-life 25 years. So I know this is going to be my H. All right, let's continue. So what else do I have here? So I know H is 25 years, so everything will be in terms of years. Find the mass remaining from a sample of 18 milligrams. So sample of 18 milligrams, this must be my A. After 70 years, this must be my T. So here I'm going to have A is 18, and T is 70. All right, so formula is M of T is equal to A 1/2 T over H. So I'm going to plug in what I know here. So M of 70 is equal to, my A is 18, 1/2. And you're going to have 70 over 25. Put this in my calculator. And I get approximately, go to 2 decimal places, 2.58. Therefore, after 70 years, 2.58 milligrams remain of strontium. All right, let's go to the next question. How long will it take for this sample to decay to 4 milligrams? So this right here is actually going to be my M of T. So what do I want to solve for? I want to solve for T. So this is going to require a little bit of some new math here. There's my equation. Let's plug in my 4. So here I'm going to have 4 is equal to 18 times 1/2 to the exponent of t over 25. All right, well, the first thing I'm going to do is I'm going to divide out coefficients. So divide both sides by 18. What do I have then? I get here about 0.2222 equals 1/2 t over 25. Now, there's an issue. It gets really difficult when I'm trying to solve for a variable in the exponent. So we're going to have to use this new rule. And here's the rule that I'm going to show you right now. The rule is this. We're going to use log. And the other alternative is trial and error. I'm not a big fan of trial and error. So we're going to use log. Log says this. If I have log of, let's say, log of n to the exponent t, a beautiful property of log is this exponent can go down as a coefficient. So it's actually equal to t log n. How does that help us, Mr. Wills? Well, if I log both sides, so I'm going to log this side here. So log of 0.2222 is equal to log of 1/2. And here t over 25. By the way, this is legit. Why is this legit? Because I'm doing the same thing to both sides. So what this happens is, because I'll have log on both sides, I can take this guy and bring him down here, which is wonderful. So what do I have then? I'm going to have this. I'm going to have log of 0.2222 is equal to t over 25 log of 1/2. Well, let's get rid of this denominator here of 25. So what am I going to do? I'm going to multiply both sides by 25. So multiply this side by 25, which gets rid of this guy. But then multiply this guy by 25, so I'm just going to put a 25 in the front here. Hopefully I've got room. And there we go. So what do I have now? So now I've got this. Oops, I wanted to make this blue. So then I've got 25 log 0.2222 is equal to t log of 1/2. Well, I want to get rid of that log of 1/2. I want the t by itself, so I'm going to divide both sides by log of 1/2. Divide this side by log of 1/2. So then I know that t will be equal to 25 log of 0.2222 divided by log of 1/2. When I put this in my calculator, I get approximately equal to 54.25. So again, we're using this brand new rule here. So therefore, write a therefore statement. Therefore, we'll take 54.25 years for the substance to decay to 4 milligrams. All right. Last note, homework. So homework, just do questions 1 to 8. So there are more than 8 questions here, but just do 1 to 8. Answers are in the brackets. 9 to 16 will be done in lesson 7. Thank you for listening.